This video is about the idea of a current source, and later on we're going to look at a current sink, and it's what those words mean. I've built this circuit, which is a comparator circuit. I didn't have to choose a comparator circuit, but on my website I introduced the idea of source and sink in the comparator section, so I've chosen a comparator circuit. I could have built a logic circuit or a counting circuit or a timing circuit, and I've set up a voltmeter, and my voltmeter is measuring the output from my circuit, and it's labelled Vout, and at the moment it's 1.29 volts. And here is my circuit diagram. I've set a 10 volt power supply, I've got my comparator circuit, which I'm not going to really talk about, and here is my Vout, which is currently 1.3 volts, and the LED is not on, clearly not on. And if I want to turn the LED on, I adjust my comparator circuit and the LED comes on, and the reason it comes on is because the output voltage has gone up. It's gone up to almost 9 volts, so my Vout is now 9 volts. And my question is, the thing I'm really interested in, is what's happening to the current, what's actually happening here. So when the LED is on, this is 9 volts. So let's have a look at where the current comes from. So the current starts from the power supply. The power supply sources current in the same way that a river source provides, is where the water comes from. So the power supply sources current. Current flows into the op-amp through the power supply. Okay, it flows through the internal workings of the op-amp, or whatever chip I'm using, through the LED, which makes it light up, through the current limiting resistor, which stops it catching fire or something, and then goes back down to 0 volts, back to the power supply. So this is the route that the current takes. The power supply is a current source. It doesn't actually matter what the rest of this circuit is. I can put that away. All that matters is that my active component, my op-amp in this case, is a source of current. The circuit we've just looked at is very familiar to us. It's this circuit here. And the reason the LED lights up is because there is a potential difference of 9 volts across the LED and the resistor. That 9 volt potential difference is provided by the output of the op-amp and means that current can flow. But what happens if we didn't have this circuit? What happens if we had this circuit? And now we're looking at the idea of a current sink. Now a sink is something like a sinkhole where things go down, or the sink in your kitchen where water goes down the drain. And I've rebuilt my circuit. Here is my LED is now attached to the positive rail. See, here's the positive, it attaches to the LED, and then the resistor goes along into the input, into the output of the op-amp. And that doesn't seem to make sense, because surely an output should give things out. Well, not necessarily. The output, this pin here, is just whatever's controlling the output device, and the output device in this case is the LED. The whole point is that current can flow into or out of the output, and we're used to current flowing out of the output. It makes sense to us, but current can also flow into the output. Let's have a look and see what happens. Here is our output voltage. At the moment it's 9.4 volts. So we've got 10 volts just here, we've got 9.4 volts just here. There's only a 0.6 volt potential difference across the LED, so the LED doesn't light up. If we want the LED to light up, we need to make this point here much lower. We need to make it a lower voltage. So if we adjust our potentiometer circuit, our potential divider circuit again, so the op-amp responds, then what we find now is that the output voltage has gone down to about 1.6 volts. So this time, when the LED is on, the output is about 1.65 volts or so. And that means that the potential difference across here is around about 8.4 volts. And that potential difference means that current can flow. But the question is, where does the current go? Well, the current still comes from the power supply. The power supply is still the current source. It flows through the LED, making it light up, through the resistor, into the output of the op-amp, through the op-amp's internal electronics, down through the power supply connection of the op-amp to the 0 volt rail, and back along this way to the power supply. So here, this pin on the op-amp is acting like a current sink. It's allowing current to flow in. So when the output voltage Vout is low, you get a potential difference across the LED. Current can flow from the positive power supply into the chip and down to ground. The LED lights up. The output here still controls the output device, but current's flowing in. That's what it means to have a current sink. And once again, it doesn't really matter what the electronics is at this side of the board. That's just an example. This could be a logic gate, it could be a counter, it could be a 555 chip, it could be anything at all. So that's what it means to have a current sink.